afternoon, and thanks to the organizers for the invitation. I'm quite happy to be here, and this is actually the first project sort of that I got involved in magnetics model, so I'm particularly happy to present it here. It's a joint work with Felix, who strategically hides in the background, and Tsatsoulis, who was at the time also a postdoc in Leipzig and is now postdoc in Ried. So let me start with a bit of introduction about what the magnetization ripple is. So I took a few pictures here from Hubert Schäfer. So the magnetization ripple is a microstructure that's formed by the magnetization in a thin film ferromagnet, and you can actually see it here in the picture. Of course, here you see the cross-tie wall and then this fine ripple structure here, which is what I want to describe today. In these pictures, it can actually be used to read off sort of the main magnetization direction, because the ripple is a characteristic phenomenon which is always orthogonal to the average magnetization direction. And from a point of view of where it comes from, it's triggered by the random orientation of the grain. So we've seen some polycrystallinity already in the morning, so that's really the background of where the ripple comes from. And what I want to focus on today is the universal character of the ripple, in the sense that it doesn't really depend on how precisely your material looks like, how the grain distribution looks like, but the ripple itself presents this universal character. We'll see this picture again, which is sort of a typical model which we have in mind for polycrystallinity. Let me, in a few slides, briefly explain, we've seen the Landau-Lifshitz functional already, how to sort of derive heuristically an energy functional which is suitable to describe this ripple phenomenon. And let me start here with the four contributions to the energy, the exchange part, the anisotropy, which will actually be the part I will focus on in particular, because it's one of the most important parts here, and it's also the part where the randomness comes in, the stray field energy, and we will put ourselves in an external field. And let me fix a bit the geometry at the beginning. So we will think of here a thin film sample, which sort of is oriented in the x1, x2 plane. The thickness is in the x3 dimension, and we will assume that it's very thin. Here I drew a sketch of the polycrystallinity, so you can think of the easy axis as really sort of a random field which takes a random orientation constant random orientation in each of the cells, but varies from grain to grain. To make the model a bit simpler and forget sort of many of the background things, let me put our sample actually in an external field that sort of fixes the main magnetization direction, and we will study oscillations around this main magnetization direction. And this is done by putting a field in the, say, x1 direction. And we will also think about this sample here sort of infinitely extended in the sense that we don't want to care about boundary effects. So with this sort of sketch of the geometry in mind, let me do some reductions that lead to the effective energy that I want to study. So first of all, working in a thin film geometry, we can assume that the magnetization is only an in-plane magnetization. So it only has components M1, M2, which live on the plane. Notationally, I will write for these in-plane variables always a prime, so that as a first reduction we can replace every m sort of by this two-dimensional vector m prime, which lives on the plane and takes values in, well, now as 1, since I reduced by 1 dimension. If you do that, you can rewrite all the integrals here. Many of the integrals you will not see the x3 integration anymore, and it just gives us the thickness of the sample. Let me stress, however, that we still have some x3 dependence here in the anisotropy, which I just integrate out, split up here, and yeah, here just rewrote the anisotropy term in this way. And we also see, okay, that's only in the next step, so that's now just reducing everything to the different geometry. Now, as we've seen in the picture, the ripple is a phenomenon that is predominantly longitudinal, so the x1 scale is much smaller than the x2 scale, which is why in the next step I just neglect the d2 of this m prime magnetization with respect to the d1 m prime in the exchange energy, and also use that the h2 component of the field is much more strongly suppressed than the h1 component of the field to reduce the exchange energy even further and disregard the H2 component here in the field and also in the equation that gives us the field. If you do that with a calculation, you can actually see that you can write the field energy as this characteristic negative 1/2 gradient, which is now only a d1 derivative of the divergence of m, which is the in-plane divergence of m. And let me further assume that the ripple amplitude is small, so we're really dealing with small oscillations around the state that is given by the external field, namely the 1,0 magnetization. So if we assume that, we can do two things. First of all, we can use the unit length constraint and just expand the square root, so m1 being given by the square root of 1 minus m2 squared, expand the square root to approximate m1 by just 1 minus 1/2 m2 squared. And in the energy contributions in exchange and anisotropy energy, just replace m1 by 1, and in strained external field contributions, replace m1 by, well, this finer approximation 1 minus 1/2 m2 squared, which then leads to the following energy, where here I'm just left with the E1, E2 component. I replaced one of the m1s here by 1 and still have an m2 here. And here in the field energy, replace the in-plane divergence just by the d2 m2 minus the d1 m2 squared over 2. What we can also see from this term here, that in this effective regime, the crystalline anisotropy really acts as a random, because E1 and E2 still are given by a random field, like a random transversal external field, which is this Q1 over T integral 0 T of E1 E2 component integrated with respect to the x3 direction. And so here we really have this interaction with a random field of the m2 component. Now, I will do a few more simplifications, which I will not write down explicitly. So first of all, let me assume, so as I said, we don't want to take into account boundary effects. So I would like to consider everything on the plane. Well, actually, the noise that we are interested in, so in the end we want to, assuming that the, let me maybe go to the next slide to already get a feeling, to assume that the grain size is much, much smaller than the typical length scale of the ripple, so that in here I will actually assume that the noise only triggers small scale oscillations, so that I can forget more or less about what happens in the large and put everything on a torus. That's the simplification I want to do. And once I put everything on the torus, I don't really need this stabilizing m2 squared term here, so let me just drop it out, so that in the end I will have three main contributions. The one that comes from the exchange part, the random external field interaction from the anisotropy, and the stray field term. And okay, there are a few reductions you can do, choosing the right sort of combinations of material constants. Let me just hide that and give you the final energy that I want to consider in the talk, which can be shown somehow self-consistently to be the relevant energy. So it consists of the exchange energy, and let me, for notational convenience, write U now for the M2 component of the magnetization. So we have an exchange part, we have this non-local stray field energy, which has this Burgers type nonlinearity here, which came from expanding the square root, and we have the noise part, which is the interaction with this random external field, which comes with a strength sigma, which sort of captures everything in a non-dimensional way. This random field we will actually assume to be of white noise character, which is in line with the picture that I had in mind. So let me just quickly go back a few. No, that was a bit too far. Computer is not very responsive. Let me stay with this. Okay. Let me stay with this picture here. Okay. So if you look at this picture here and really zoom out, it's not hard to believe that on very large scales you will see a field that pretty much looks like white noise. And that's the reduction I want to do. Let's assume that our field is actually given by white noise. Let me stress here that the noise is really of a quenched character, so it's no thermal fluctuation that we're considering here, but really the effects of these randomly oriented grains in the material. It's an isotropic noise, and the model we will put in is sort of what we have in mind is you just say use a Poisson point process to throw in uniformly points in the plane, and then do a tessellation by say Voronoi cells, and in each of the Voronoi cells you uniformly at random throw in an orientation vector. That's sort of the model we have in mind, and that if you zoom out leads to an isotropic random field, which nevertheless, due to the non-local interaction given by the stray field, leads to sort of an anisotropic response of the magnetization. Now, once we have this energy, the first step is sort of to see, okay, what can we say about minimizers? And let me actually look at the Euler-Lagrange equation, which reveals somehow subtleties that come from replacing our random field by a singular object like white noise. So formally, the ripple is described by minimizers of this energy functional, which sort of, let me go back to the energy, has an harmonic part, which leads to an elliptic operator, which is sort of non-local because of this negative half derivative. There will be some nonlinear terms, and there will be a linear term coming from the white noise, a constant coming from the white noise. So it's not hard to believe that this is actually the Euler-Lagrange equation, which has a non-local second-order elliptic operator here as its linear part, some non-linearities, and on the right-hand side we have white noise. Well, projected white noise because I'm working on the torus, and in order to have finite stray field energy, we have to assume that we're working with functions that have zero average in the x1 direction. Otherwise, the stray field energy is infinite, so that's something I will always assume. So that's where more or less this projection of the functions with 0 and x1 comes from, and I used notation R1 for the Hilbert transform, so D1 is the modulus of D1. Now, if you look at the equation, let me convince you that this is actually an equation which has problems. It's a singular stochastic differential equation. Let me walk you through the steps that show that this equation really has problems. First of all, since we sort of have an anisotropy in the leading order operator, it's somehow natural to endow the space with a metric that is homogeneous with respect to this natural scaling that is anisotropic. And if I scale in the x1 direction by L, I have to scale by L to the 3/2. If I do this, so if I use sort of a Cardano-Theodori metric which respects the scaling, on a heuristic level, what happens is that if I count derivatives in x1 and x2 direction, they're worth, so they cost differently. So in particular, if I take an x2 derivative, it costs 3/2 an x1 derivative. and which also leads to the fact that in terms of the dimensions, or the effective scaling dimension, it's not 2, but 1 plus 3 over 2, so 5 over 2. This scaling dimension is important because we're dealing with white noise here, and from the effective dimension you can actually read off the regularity of white noise, and we will see that this right-hand side here is just too irregular to make sense of at least some of the nonlinear terms here, especially the one that are marked in red. So we will see that this term is actually a dramatic term. So for the next slide, let me forget about the other terms. They're sort of fine, and just focus on this simplified equation for now. So as I said, white noise, the regularity of white noise, you can read off from the dimension in the sort of folklore that the regularity, so first of all it's a distribution, and its regularity in the scale of suitable Bezow, or in our case anisotropic Bezow or Hölder spaces, is given by minus this effective dimension over 2 up to an arbitrary small epsilon, which in our case means that we can expect C to be a distribution of regularity minus 5/4 minus, almost surely measured in this anisotropic Hölder, in these anisotropic Hölder spaces. Now L, as we've seen, is a second order elliptic operator. Okay, it's non-local, but one can develop a regularity theory, in particular Schauder theory for this operator L, which goes back to a previous work by Ried and Felix, which shows that this operator L improves regularity by the expected amount, namely by 2. If we do this and disregard this nonlinear term here for now, then just looking at the linear equation, we see that U should essentially have regularity minus 5/4 minus plus 2, which is 3/4 minus. And then we have a problem, because D2, we saw, doesn't cost 1 derivative, but actually 3 half derivatives. So if I act with the D2 on the U, I lose 3 over 2, which gives me minus 3/4 minus. Okay, the R1 here as the Hilbert transform is essentially a zero order operator. On this L infinity scale you lose an extra epsilon, but that's not really important. So that R1 D2U is a distribution of order minus 3/4 minus. But then you want to multiply it by a U, which only has regularity 3/4 minus. So you sort of borderline miss the case where you can define this product here in an unambiguous way. So there's a problem here. This U R1 D2U is sort of too singular to give it a sense, and we have to do some renormalization. Let me actually stress that the problem is really this R1 here. If it weren't there, then we would have something like a U D2U, which is a D2 1/2 U squared, and that could be perfectly well defined. So it's really the R1 here that comes from the Hilbert, so from this negative half derivative, that creates troubles here in defining this term. And that means that we have to find a good renormalization procedure to give sense to this term in the PDE. The good news is that it's only borderline singular, so we only miss half a derivative, so there is hope that the renormalization process is actually not too dramatic. And as a first sign of this, let me mention the sort of previous work by Ried and Felix, who analyzed the problem on the equation side, and by a Dabrato-Debisch strategy, which is similar to the treatment of Dabrato and Debisch of the 542 model, is that they sort of split off the linear solution and study oscillations around the linear solution, and then you can actually set up a fixed point argument for the remainder part, at least for small values of the noise sigma. And the way one can treat, assuming that everything is sort of a Gaussian noise, the way to treat the singular product here, which now here, as I wrote it, so V in my talk here will always denote the linear solution, so the solution of LV is peak psi, for which it really has the nice Schauder theory. So this product here is ill-defined, but by a renormalization, which is sort of take your noise, smooth it, say by a smooth kernel phi L by a convolution, and then look at the product and subtract a divergent term, which actually by symmetry turns out to be 0, to define, at least in a stochastic sense, this ill-defined product in the limit when the regularization parameter goes to 0, and then combining these two parts, sort of a deterministic fixed point argument and this probabilistic construction via Victor normalization allowed them to conclude that there are solutions of the problem. Now, we actually want to study sort of what happens if this parameter sigma here is large. And then, but let me first show you another drawback, namely that the construction here they used via classical Victor renormalization, in particular the smoothing by a kernel, the analysis depends a lot on Gaussianity. In particular, the Gaussianity of the approximations of white noise that always use sort of Nelson's hypercontractive estimate to control higher LP norms just by L2 norms. But as I said, what we have in mind somehow as a typical grain model is this Poisson point process, Poisson-Voronoi tessellation, and then random orientations in each cell. This is a problem that is far from being Gaussian. So one of the motivations that that led us to what I will show you next is really how can we leave the Gaussian realm and really find a framework where we can also say something about models which are sort of still converging to white noise but leave the Gaussian realm. Yes, as I said, this suitably rescaled still converges to white noise, but it's sort of a non-Gaussian approximation of white noise. And before going back to the energy, let me already show you what the class of probability measures that we use, the class of approximations we use, that's given by the following. Namely, we look at probability measures on the space of Schwarz distributions that are, okay, first of all, centered. They satisfy stationarity assumptions, so the law doesn't depend on shifts. And it's invariant under reflection, so that was somehow a subtle point here. Okay, it really jumps a few slides. Okay, so that was a subtle point here due to a symmetry. This renormalizing term, which typically leads to a divergent constant, that was here 0, and we also want to include this symmetry in our model. So let me assume that we have an invariance under reflection, say from x1 to minus x1, so that this transformation doesn't change the law of our random variable. And then what we want to replace the Gaussianity by, and that's not a crucial part, is a spectral gap, also infinite dimensional quantum inequality, which says that the variance of certain suitable nonlinear functionals of Xi, of the noise, is controlled by the expectation of the L2 norm of the derivative of G with respect to the noise. That actually leads to nice concentration properties, and one can show that it's sort of a good replacement for Gaussian calculus, because having this on an L2 level, you can also derive it on an LP level for any P. And this is a class of noises, models for our noise, that includes white noise. That's a classical result. And one can actually show that the spectral gap inequality sort of is in the background that tells us that our noise is again supported on the class of distributions with the right regularity, namely -5 minus. So that's the sort of models I have in mind now, and now we really want to study the universality of the ripple, so that the ripple phenomenon actually doesn't depend on what precise representative of noise in this class I take. Somehow it always jumps too far. Okay, so as I said before, we want to do this in a regime where we're not in a small noise regime. So let me actually forget about the sigma parameter and just set it to 1 for simplicity. And now since we don't expect, since the energy functional is non-convex, and since we don't expect minimisers to be unique, it's actually a much better idea to look at the problem on the level of the energy functional itself. And we want to sort of study the universality in a variational approach based on the direct method, and express the universality also at the level of the energy and not at the level of, say, the equation. Now here again is the energy, but let me show you a few problems that one has to face when working with the energy. And the first one looks pretty dramatic, namely that the total energy, if you just look at the linear solution, that is actually almost surely minus infinity. So at this step you could say, well, okay, there's no chance to do it with the direct method, let's just go home. But actually it's not so bad, because that's sort of is the only divergence that appears. So, okay, here this is sort of another law of white noise. If you just subtract this divergence here, if you subtract the total energy of the linear solution, then this is actually the only problematic term, and by shifting the energy by this infinity, you end up with something that is well-defined. Well-defined if you sort of think for the moment of having a smooth noise, so that this product here, which still is problematic from a different point of view, is well-defined. So after to subtract this infinity, we end up with an energy which is actually nicely behaved. Let me split it into two parts, sort of this anharmonic energy, which has the exchange part, and the stray field energy, which still has this Berger's nonlinearity in here, plus a remainder. And what I will show you on 1 or 2 slides is that one can analyze this anharmonic energy quite nicely, but it turns out that one has to rely, to get compactness, one has to rely on the very subtle cursivity properties of the Berger's operator. And in particular I want to show you the Kalman-Hobart-Monin identity, which is an identity which comes originally from the fluid mechanics community that sort of allows us to extract these subtle cursivity properties in this anharmonic energy to get the deterministic convergence statements. But we have a second problem. And the second problem is that we still have this VR1D2V, this singular product, in our energy, in particular in the remainder term here. And now we cannot rely on Gaussianity, so the classical micronormalization doesn't work. So we somehow have to impose a renormalization rule, somehow stating what do we understand by this product VR1D2V. Let me for now just replace this product here by an object F, which, well, definitely cannot be, from the point of view of regularity, cannot be better than the worst part here, which was the R1D2V, which had regularity minus 3/4 minus. So let me impose somehow a renormalization rule. Let me be a bit vague at the moment here and just say, okay, we can replace by a good procedure this product here by an object F, which actually in the Gaussian setting we saw can be constructed by micronormalization. And what I will later show you is that this renormalization procedure that very heavily depends on the spectral gap inequality to handle the non-Gaussian setting. But for now, let me just say that we can do that somehow and end up with an energy functional which is now sort of parametrized by the noise, or by V, which is sort of in one-to-one correspondence with the noise by the solution of the linear equation. This sort of replacement of the ill-defined product, and it's a functional in terms of W. So I forgot to tell you here is that we now, having subtracted this divergent energy of the linear solution, let me look at the whole thing as a functional that again studies sort of deviations from the linear part, so a functional in this deviation W, and as we saw here, this leads to this nice anharmonic energy of W, and the remainder part, which sort of has as parameters this V and now this replaced a singular product, and is a functional W that lives on sort of the natural space where one can study this energy functional, namely on all functions in L2, say, which have finite harmonic energy, or using the cursivity estimates that we can extract from the Harman-Wolfram identity, that's equivalent actually to working on a space where we have finite anharmonic energy. And now what I want to show you next is how one can use the topology of gamma convergence, which is sort of the natural topology once we set up everything on the space of functionals. We can really give a sense to the law of this energy in a way that is independent of how we approximate white noise within this class of probabilities that satisfy the spectral gap inequality. And that's the statement. So taking any stationary centered probability measure that satisfies this parity symmetry x1 to minus x1 and the spectral gap inequality, we can extend it to a probability measure on the product space of distributions Xi and lower semi-continuous functionals on the space W, which is sort of the natural space where we consider our functionals, endowed with the natural topology, namely that of the gamma convergence, so the gamma convergence with respect to the strong L2 topology, such that the following holds, namely that the law of Xi under this extended measure is still the one we started with. So we have a nice projection property. If Xi is smooth, almost surely with respect to our probability measure that we drew from this class, then actually the energy that we can now sample from this extended measure turns out to be the one which is exactly the one that one would get if one just takes the now classically defined, since Xi is smooth, the classically defined product V R1 E2V. So we have some consistency property. And most importantly, if I now take a sequence of probability measures in this class that converges weakly to a limiting measure, and I really want you to think of this limiting measure as being law of white noise. So if we have an approximation of white noise in this class, then looking at the extended measure on the space of X's with energy functionals associated to this Xi, we have a continuity, namely that the extended measure corresponding to the approximation of white noise converges to something that we can sort of think of as the energy functional that would correspond to white noise as a limit. And again, this is sort of consistent in the sense that if Xi is smooth, is a smooth realization, then we coincide with the classical setting where this VR1D2V is classically well defined. As a corollary, we get existence of minimisers. So for almost every pair of noises and energy functionals under this extended measure, we can show that minimisers of E exist in the space W, and we sort of have an estimate that is consistent with studying the Euler-Lagrange equation for this W, namely that this W satisfies in some sense a 5-quarter minus regularity. I don't want to spend too much time on this, so let me rather show you how our analysis can be understood sort of in an analogy to the rough path theory, where we have sort of a probabilistic step and a probabilistic step and independently somehow deterministic step. So once the probabilistic setup is done, we can do a fully deterministic analysis. And if you remember Felix's talk from Monday, there was also sort of this strict splitting between probability and deterministic arguments in the background. So that once we construct this renormalization, this renormalized singular product in a consistent way, then we can sort of take our noise Xi, lift it now to an object that combines Xi with, okay, I keep the V here, which is sort of redundant because Xi and V are in one-to-one correspondence. We can sort of enhance our objects by this renormalized product. And here you can really think of somehow the similar thing what you do in rough paths. If you look at say Brownian motion and its iterated integrals, so there's also an enhancement going on. I tell you a good construction of this ill-defined product, which is consistent and allows us to study the next step, namely how to take these extended objects and associate good functionals with it in a deterministic way. That is somehow this rough path analogy here. So how do we construct the F? Well, we do it essentially like one would expect, similarly to the vector normalization that I showed you before. We will just smooth our V, subtract sort of the dangerous constant, which is the expectation, but by parity we can show that, again, this is actually 0, and show that at least in a probabilistic sense, so in LP with respect to probability, but then in the Ried regularity class, which was -3/4 corresponding to this R1 D2V term here, we can construct this limit here as an object, as I said, in LP with respect to probability with the Ried regularity, such that if you now insert it in a deterministic argument, namely you just take these enhanced data, Xi, V, and F, and use a completely deterministic analysis on a deterministic level, the continuity that one can show with the nice properties of the renormalized energy, that you have continuity of the map that associates a Xi-V-F to the corresponding renormalized energy, that this is continuous with respect to gamma convergence. You can just rely on this continuity and push forward the measure that now is sort of the extended measure on triples to a measure on X's and renormalized energies. And that's exactly what we saw in the theorem. And we also have a sort of consistency in the sense that if Xi is smooth under this probability measure, then the product VR1 D2V is well defined and it coincides with F. So let me highlight a little bit the deterministic ingredient, which is an a priori estimate for the inviscid Burger's equation, which in this setting here goes back to the work of Goldman, Josiah, and Otto, which is essentially this identity here, which can be seen as a Karman-Hobart-Monin type identity for the Burger's operator, which is an explicit calculation that you can do. And what's interesting here is that it sort of reveals a hidden cursivity in the sense that looking at this object here, you can see that somehow by working out the details, you more or less gain, well, not a full derivative. You have to be a bit careful about the, so D1H here is sort of a discrete derivative in the x1 direction. If you work things out, what you can see is that on an L3 level, you gain half a derivative. So if the energy is finite using this identity here, what you can show is that your W actually has half a derivative in the x1 direction, which lives in L3. And this you can use to control, first of all, the harmonic part of the energy by a suitable power of the anharmonic energy, which also reveals that you not only with the energy control the D1 derivative, but a fractional derivative, namely a 2/3 fractional derivative in the x2 direction. And that's sort of the compactness that you gain from this Karman-Hobart-Monin identity, which is in the background of our deterministic analysis to show gamma convergence. And let me mention here that these estimates basically analogously have recently been applied in a 2D smectics model in a periodic setting by Novak and Jan to also derive the crucial compactness properties in a similar way here. So their energy, instead of a negative half derivative, has a full negative derivative, but the analysis is essentially the same. And again, it's based on a compactness that is gained by this Kalman-Hubbard-Monin identity. So what's next? As I said, we sort of, for simplicity, wrapped everything on the torus. Actually, it would be nice to study the model on the full plane, because that is sort of the physically more interesting setting. It would reveal a scale invariance and sort of really say that this ripple essentially only depends on one parameter, which is sort of the variance of the noise. But that's not very clear. Of course, then you have to add back in again this stabilizing external field term, but then it's not so clear whether you can sort of do in a consistent way this infinite volume limit. So that's something that we're working on at the moment. And actually I was cheating a bit in what I told you, because I said that somehow the model for the randomness we have in mind is this throw in Poisson points, do a Voronoi tessellation, and add uniformly random orientations in each cell. That is actually a randomness that slightly misses this class of satisfying a spectral gap inequality, in the sense that one can show that it does not satisfy a spectral gap, but a variant of the spectral gap inequality, which is so-called multiscale spectral gap inequality. So you use somehow the strong decay of correlations that you have in the Poisson-Voronoi tessellation to show that you sort of, when looking at local variations, you still have sort of a spectral gap inequality, which could get worse when you increase the window that you're looking at, but then the decorrelation of the Poisson-Voronoi helps you bring it down exponentially. That's inequalities that recently have been studied by Michael Dumanx and Antoine Gloria, and we started working out the details that also multiscale spectral gap is sort of a good class of probabilities that that can be used in the background of approximating white noise. So what we have is that indeed this model is an approximation of white noise, but our estimates still don't work on the probabilistic side to give this good renormalization construction that again, combined with the deterministic analysis, gives you the existence of the ripple. Okay, that's all I wanted to say today. So I showed you how to use gamma convergence techniques to study the universality of the magnetization ripple in an approach that is deeply connected to the normalization of singular SPDEs, which is somewhere in the background because of the Euler-Lagrange equation that is singular. The novelty is that we can really set up a rough path type strategy in the calculus of variations that allows us to, in a non-perturbative setting, really study this universality. And on a conceptual level, what's nice is that we somehow transfer the methods that have been developed for thermal noise, so Haider's theory and so on, to the realm of quenched noise, which on the probabilistic side heavily depends on spectral gap inequality to handle the non-Gaussian setting, but still have something that has nice Gaussian concentration properties. And on the deterministic analysis has this subtlety that we have this Burgers operator in the background and need the Kalman-Hubbard-Monin identities to extract the good cursivity properties and Schauder estimates for nonlinear. And with this, thank you for your attention.
Thank you very much.